Good day, guys. This is Chapter 4, Lesson 2 in our never-ending bouncing around between math books. And the title of this section is called Critical Attributes of Similar Figures. That basically means the important things you need to see and know about two shapes to know if they are related or similar. That's basically what all that means. And as usual, we'll cover and discuss this first page in class, which is page 321. So let's go ahead and move right into our information and our examples on page 322 for this video. Now, on page 322, our key concept is called identify similar figures. This is how you're going to know if two shapes are similar or not. And that's going to be the first step in this whole lesson. So it tells you here in the definition, if two figures have congruent corresponding angles and the ratios of their corresponding sides are equivalent, then they are similar. Let me explain to you what that means, because that's quite a lot of words that might be new or unfamiliar to you. So let's start off with the first part. If two figures have congruent corresponding angles, that means angles that match each other exactly. For example, these angles in this order match exactly these angles over here. So they are congruent, they match, K to P correspond, L to Q correspond, H to M correspond, and J to N are corresponding. So they are equal and matching angles. That's what congruent corresponding means. It means equal and matching. And by matching, I mean they're in the same place as the other angles are with their shapes. And it says, and the ratios of their corresponding sides are equivalent. And that's what we're going to talk about right now. Ratios of corresponding sides. For example, they took some ratios, and remember, ratios are basically fractions, and they measured some sides. They said, from the big triangle, rectangle, we have side MN, which is this side right here. Its length is 10. From the smaller rectangle, now since M and N is on the bottom, and it goes from right to left, that means it corresponds to HJ, which is also on the bottom, and goes from right to left, and its measurement is 5. The ratio 10 over 5 can be reduced to 2 over 1, or just 2. Once you've found out how two shapes are related, let's say big to small, like we did here, then you could find and check if the other sides are also related in the exact same way. Because if they are similar, they should also be related in the exact same way. And we'll go ahead and look at the next ratio, N to P, which is this left side from letter N to point P up here, and that has a length of 6 units. That corresponds to JK, which also has a side length of 3. 6 over 3 simplifies also to 2. And you can repeat this process for the other sides of your shape, and as long as you get the same number or the same ratio every single time, then you know they're similar. The ratio will not always be a whole number. It could be a fraction. For example, let's say I want to compare, instead of big on top to small, the reverse, small to big. So I'll take this top side, K to L should correspond to P to Q. And it does, according to everything we've seen here. KL has a length of 5, and P to Q has a length of 10. Simplify that, and I get the number 1/2. So why this number up when I do it this way, and why this number when I do it this way? Well, here's what that's telling us. If I go from small to big, like I did here, that's telling me the small triangle is 1/2 the size of the big triangle. Over here in these examples, I went from big to small, and I kept getting the number 2. That means this rectangle, and I think I said triangle before, excuse me, this rectangle is twice as big as this rectangle. Please forgive me if I use the wrong words by accident. I am talking about rectangles in this example. So that's how you can prove it. You can compare sides between two shapes, and if you get the same measurement or the same ratio every time, then you know they're similar. It's important though, like in this example, if I go big to small, then all my other comparisons of ratios have to also be big to small, big to small, big to small. And we will practice that some more. Now it goes on to say that figures that have the same shape but not necessarily the same size are called similar figures. And all that means is that you have two shapes that look alike but are not exactly alike. They're similar, not exact. That's all that means. Here it tells us rectangle HJKL, that's how you name it, above is similar to rectangle MNPQ. Two things you need to know. When you write, whenever you're introduced to shapes with letter names, the letters have to go in alphabetical order. So H, J, K, L. Yes, they skipped the letter I, and you can do that. You can skip letters, but still alphabetical order is similar to M, N, P, Q. They left out the letter O here also, but they still went in alphabetical order. And we're going to talk about how that's important more in the next example. And it tells us now, this is written as rectangle HJKL is congruent to rectangle MNPQ. This little squiggle sign means that two things are, actually not congruent, I used the wrong word. This little squiggle sign means that two shapes are similar. That's what that means. Now let's go ahead and use what we just talked about up here to do our first example. Now, in example 1, they want us to test whether these two trapezoids, A, B, C, D, is similar to trapezoid HJKL. And there's two ways you can do that. I'm going to go ahead and clear the screen up. And let's go ahead and practice the first way. The first way to do it is you can compare two shapes and matching sides. I know that the first the first trapezoid is called ABCD. And the second trapezoid is called HJKL. Excuse me. Now, what you have to know is whenever you're given two shapes that we think are similar, and they give us letter names, the letters have to also match or correspond to each other. For example, from A to B, which is this distance down here, has to match up with H to J, because these are the first two letters in alphabetical order, and these are the first two letters in alphabetical order of our second shape. A to B has to match H to J. And we can see that that's true. Although this shape has a little side facing to the right, this similar shape, or at least we think it's similar, has its little side facing to the left. So it's just flipped over. But A to B matches H to J. So I'm going to go ahead and talk about that relationship first. I know AB on the big trapezoid corresponds to HJ in my little trapezoid. Let's go ahead and take those measurements. A to B is 10 kilometers. Therefore, H to J is 4 kilometers, according to the data. Now, 10 to 4, this ratio can be simplified to 5/2. This is now an improper ratio. Let's go ahead and make it a mixed number. 2 goes into 5 2 whole times with 1 left over. So 2.5 is my scale factor. That's my relationship. I can safely now say, because I went from big to small, that this big trapezoid looks like it might be 2.5 times the size of this smaller one. But I'm not sure yet, because that's only if they're similar. I only compared two sides. I need to compare at least another set of sides, which I'll go ahead and practice on now. So let me go ahead and change my color up here. And I'm going to go ahead and compare this side, this long side. So this long side goes from A to D. From A to D. That means I have to compare it to H to L. H to L. And they do match up, thank God, because if they didn't, then I know something's wrong and they're probably not going to be similar. So I'm going to compare A to D to side HL. H to L. Well, A to D is 5 kilometers long, and H to L is 6 kilometers long. So AD, 5 kilometers, HL, 6 kilometers. Now, I'm having a bit of an issue with this, but let's go ahead and keep looking at it. So 5 to 6 cannot be simplified. Excuse me one second.